Ladies and gentlemen, very welcome to this Biosolve IT webinar. My name is Markus Gastreich, and I have a helping hand by the side, namely Dr. Carsten Detering, and the two of us will guide you through this webinar. Currently, we are muting everybody so that we don't have audio artifacts in there. And in case you would like to ask something, etc., we have a little chat box in the GoToWebinar control elements, as you will probably already have seen. So hopefully video and audio is good, and I hand over to Carsten Detering for a few introductory words. Carsten?
Yeah, good morning, everyone. Welcome to Biosolve IT's webinar series. Today's topic will be Living a Dream in Silico LO for Medicinal Chemists, an introduction to visual and interactive design. The featured product in this webinar is CSAR, which we released about a year ago. And the presenter will be Markus Gastreich. He has a background in theoretical chemistry, namely quantum chemistry. He has a lot of experience with force fields, so he's the right person to tell you about CSAR, which is not based on force fields, but which is very strong in the application of scoring functions. So with this, I would like to hand over to Markus, and please enjoy the webinar.
Thank you, Carsten. So just so that everybody is actually in full picture, we are split apart by several thousand miles actually, and Carsten is currently sitting, probably enjoying a fresh coffee in Washington State, in the very northwest of the USA, whereas I'm based in the western part of Germany, close actually to the Dutch, Belgian, and French borders, in the vicinity of the former capital in Bonn. So as Carsten already mentioned, both of us are trained in chemistry, and of course we are extremely keen and interested in getting to know who actually you are. So GoToWebinar actually gives us the possibility to do a quick polling, a quick questionnaire, and with this I would like to try to actually launch this and get it going. So you should currently see the question of who you are and what you do, what a profession you are. So as it appears, the answers drop in here. We do have a focus on medicinal chemistry people, and this is wonderful. That's exactly what we wanted to achieve. Okay, so it's close to 80% polled. We'll wait a few more seconds.
Almost everyone
seems to converge. Okay, wonderful.
We're about to close the poll.
Let me start out with the kind of provocative statement: shall non-experts in computational modeling actually do the modeling? And with this, I would like to take a look at the past 25 or so years, let's say. So going to the next slide, where I tried to classify a little bit what happened from the 80s to today. In the 80s, I would say we'd have a lot of classical medicinal chemistry. We had many different targets. We had a lot of challenges in wet chemistry, but we didn't really have predictive computing at that time, at least not at all for everybody, or not even so on personal computers that were readily available right next to the lab. In the 90s, it became clear that there was an advent of what people call rational drug design. Many people jumped onto docking algorithms, early docking algorithms, including the 1996 first published FlexX algorithm that we still ship and have further refined and optimized, etc. And also similarity was a big thing. The daylight fingerprints, Unity fingerprints were very popular and partly still are until today. From roughly 2000 onward, it became clear that the that the field totally changed. A lot of outsourcing occurred, many mergers appeared, and several thousand people were really put onto the street. I tried to quantify this a little bit with a paper, the reference to which will pop up in a second. This is taken from a recent publication from Abu Gharbia. And if we take a look at this timeline here from 2000 until 2012, these are the mergers and acquisitions with values exceeding $2 billion that occurred from 2000 onward. And it's pretty striking what happened there. Many of you will be familiar with one or the other, and especially the big Pfizer takeovers went through everywhere in the press. Likewise, another quick view from a statistical perspective is a simple one. Just take a look at the number of members that the PHRMA actually counted. From 1988, where we had, I don't know, let's see, 2, 4, 6, 10, 12, 14, 15, 30, 40 something members. And in 2011, they counted 2, 4, 6, 8, 10, only 11. So the field has drastically changed. And the question is, what is the consequence of this actually? To our understanding, the direct consequence is that medicinal chemists will have to take over a lot of the core computational tasks now on. And down here you see the actual reference that I just referred to. Yeah. So in my opinion, if we take a look at a project, at an early drug development project timeline here, target validation, hit finding, H2L, and lead optimization. Of course, the early field is the field of bioinformatics, more so chem bioinformatics by now. And the hit finding, virtual screening things, etc., is still mostly in the hands of computational specialists, but also outsourced CROs. A lot of academics now do the screening work, etc. Computational work actually accompanies all of them, and this was not always the case, especially with the advent of new tools like pocket detection algorithms, protein-protein interface analysis, and even PPI prediction algorithms. We can now do things that we could not do even 5, 6, 7 years ago, of course accompanied by the ever-growing power of computers. Also, in terms of the hit detection, new ways of assessing affinities have emerged. Desolvation has been realized as being really important. Even entropic terms are in there in very few functions, and so on and so forth. But it becomes clear that especially at this end here, the field has, or the change of the field has the most drastic impact here. And it is also clear that MedChems are really involved in computational tasks in these late stages here of early development. And one element which really makes this strongly evident is how much money, for example, Sanofi now puts on the table to have computational chemistry almost entirely outsourced to Schrödinger at this point in time. So just looking at for example, the Frankfurt group at Sanofi of computational chemists, several years ago there were 30 people. Nowadays, I think there are 3 or 4 computational specialists left over. So we have to adopt to this scenario here. And with this, I'd just like to take a mini break again for another short questionnaire. I'm very interested in getting to know your feeling about this change and how it affects your everyday life. What's your opinion today? Should MedChems, or will MedChems actually take over computing tasks, or maybe not so much? I'll just wait for a few seconds for the answers to pop in. I'd be grateful for your vote. Yeah, that is interesting. It is not as clear as I was thinking it would be. Maybe it's also a regional thing. Computation being absolutely already a part of everyday work, so the change is not that drastic, and the other way around. So roughly a 60-40 or 55 to 40% convergence here. 56% think that the non-experts would even add a different perspective to the challenges that we have. Very interesting. Thank you for that. So, continuing here with the slides. What are MedChems' core tasks? That's the question. So we can certainly not put everything on the table of medicinal chemists because they are paid and trained to do something different, namely synthetic work and proposing SAR, etc., and so on. So if we would ever want to write something up in terms of a software that assists medicinal chemists, then we would have to do a proper analysis. What is an everyday medicinal chemist's life day like? So to my understanding, it is a lot about SAR. And SAR is mostly well understood if we can visualize data and if we can visualize structures, etc. So visualization is really at the very core of everything. This is corroborated by a recent paper that people from GSK wrote, where they did an in-house survey, which is actually published in JChemD here, late 2012. The question was, what would give you physical pain if I took it away from you? And the answer, by far, on number one, the most prominent answer was visualization. They need visualization for everything, to understand things, to predict things, and so on. So definitely, any software that is to tackle this problem needs to be a very visual software. The second point is, of course, at the center of the multi-parameter optimization procedure to make a ligand more appealing would be some kind of predicting, evaluating, assessing, estimating the activity of things, which is usually still being done using docking and scoring and other methods in the non-structure-based area here, of course. The third, I would say, would be then to propose molecular modifications, be it hypothesis-driven or driven by some other rationale. And for this, of course, a software to support this would have to help spinning ideas, also to edit and modify an existing molecule. Certainly, and at this point I left this out a little bit because it doesn't couple so much to computing, is actually the tasks of the actual synthesis and doing reporting, preparing meetings, and so on and so forth. So taking this to the next level, taking this to a meta level, if we wanted to write something up tackling those issues, then we would need something that performs docking and scoring in a state-of-the-art fashion, which translates to the software needs to have sound and relevant science. I mentioned the point of being visual, of course, that's extremely important, and helping to spin ideas and edit, modify things would be translated, in my opinion, to something which is playful, fast, and easy. It is of no use if a medicinal chemist has software on his or her desk and the results just need 2-3 hours to complete. So something very interactive and playful, which is easy to learn. So let me start with this last point here, playful and fast and easy software. I would like to introduce CISA to you and being a little bit provocative here, comparing to what's out there. So is it playful and easy if we have software which, after popping up, has 44 choices for a user to actually click somewhere? Pages in the manual for benchware, I'm not so sure because I didn't find anything online, so I just put a question mark at this point here. The next software which pops up to my mind is Mo from the Chemical Computing Group. Buttons after startup, if I counted correctly, that's about 35 possibilities there. Pages in the manual, there isn't really a PDF manual that I found, but it's HTML based and must have several hundreds of pages here. The next which pops to my mind is certainly the Maestro tool from Schrödinger, which counts 80 buttons after startup and almost 360 pages in the manual that people can read. With CISA, we have 5 buttons after startup, and we have 0 pages in the manual because there is no manual. So to be precise here, we fight for every button here internally, and we really want to keep it as minimalistic and easy as possible, as clean and slick as possible, this piece of software. Of course, you can argue But the other tools have many more functionalities. Yes, that's definitely true. These are modeling packages mostly. But then in return, I would ask from all the functionalities in Microsoft Word, what's the percentage that you really use? So our mantra is here, let's focus on the things that are really of utmost importance and add these step by step. And this is what we do. So CISA is out for roughly a year now, and we have had already 10 releases. So check back frequently to see how this baby keeps on growing. So after this small provocative excursion, I'd like to focus on what we understand under relevant science. Of course, at the core of everything would be to estimate somehow an affinity. The dilemma is delta G predictions are not reliably possible today, and I would strongly put myself into the position that you shouldn't even believe anyone else claiming that this is a solved problem. However, today we can estimate or approximate, and even if we are sometimes in situations where we are not predictive, we can at least visualize things and help the user to understand why we are not predictive and still be useful in that context. So let me give you a bunch of examples here. So I'd like to dive into a demonstration of a protein ligand complex, which has recently been published by Pfizer. It's a kinase with an inhibitor, and with this, I'm jumping out of the presentation mode here and firing up CISA in a second. So this is what it looks like. I'm going to enlarge it a little bit so that we can see a little bit better what's going on. So very minimalistic, not many things on the screen here. And we are now prompted to download a PDB code. So that's exactly what we'll do. So I'll type in 4CD0 and hit the return key. And with this, I load in the protein ligand complex. So besides the pure visualization that we can do, we have already prepared the protein, prepared the ligand. We have computed all tautomers and selected the ones or the one that makes most sense in terms of the energetic evaluation. We have computed a bunch of properties, and especially we have an estimated affinity. Now this compound has been measured to be 7 nanomolar, so we slightly overshoot here, but we are in the right region with respect to the error bars. And if I click on this line here, I'll be prompted to zoom in, and I can now take a look at this compound here in all detail. So I'll explain on later slides what's actually going on here with all these spheres and bubbles, etc. But what I wanted to convey is that we have an atomic or atom-based visualization of what's good and what's bad for affinity. So with this thing here up there with this hydroxyl group, we can see that there are hydrogen bonds being formed. I'm trying to zoom this in a little bit so that you can see things clearer, etc., etc. And before I confuse you, there are, of course, possibilities to measure distances and getting a deeper understanding of what's really going on here. So this was just a very early quick demo so that you get a feeling for what this software is actually doing, how fast or slow it is, how it's visual, etc. I'm going back to the slides to explain a little bit more. And of course, we are going to demo things. Yes, oops, I'm jumping out here. Excuse me. Oops. Switching the display. Okay. So, what did we do here? We actually computed a delta G approximation based on something that we call HIDE. In HIDE, we have an atom-based visualization of contributions to the free energy of binding, and whatever is colored in green is good for affinity, and whatever is colored in red is bad for affinity. So we can now go from atom to atom and can take a look at where the molecule is weak weakly contributing to affinity and where it's contributing strongly. The larger these high coronas, that's what we call them, the larger, the stronger that contribution or the anti-contribution. Stepping back a little bit, let's think about what is really affinity, because of course many groups on the globe try to approximate the free energy of binding. And 11, 12 years ago, we stepped back in a collaboration with Bayer and Hamburg University and thought, okay, obviously affinity is the difference between two states, or a multitude of states, let's say, but essentially the difference of something before and after. What do I mean by this? Well, essentially, the before is a state in which the ligand floats around in bulk water, at least in first approximation, and we call it unbound. And the after state is where it's bound, forming a complex. So the process associated is that we have to kind of remove that ligand and move it out of the water and put it down into the pocket, and everything associated needs to be taken into account as good as possible. So with this, I'm preparing the next poll here. Let's do a thought experiment. Let's imagine I had a protein with two cavities, two subpockets. So one subpocket here, the other subpocket here. And the two cavities are occupied by two parts of the ligand. And in the middle of the ligand, in the center of the ligand, there is a phenyl part. Ignoring all torsional rearrangement, etc., let's assume that this guy here sticks out into the solvent. Now the question is this good or bad for affinity? I'm very excited to see your votes on this. And never mind, of course, everything is anonymous, and even if you do a wild guess, nobody will tell. That's a pretty clear vote. So we have 17% saying that this is good for affinity, means favorable, and 72% claiming that this is bad for affinity. 6% of you say that doesn't really matter, and another 6% say I don't really know. Well, seeing the delta of delta G's here, we really have to take into account what's before and what's after. And if we take a look at this, then we need to see that this phenyl part here was already in water, and it still is in water. So the difference between before and after in this schematic example here is negligible. In other words, since it doesn't form any new bonds, any new interactions or so, the before state is equal to the after state, and that means that it doesn't do any contribution here. Of course, before I get misunderstood, of course, that doesn't mean that we want to achieve something like this in a drug. Of course, we would much more like to bury the phenyl part here, but from an affinity standpoint, there is no contribution, nor bad, nor good. And this is something that we would have to improve on, of course, in the drug research project. So, zooming back 12 years ago, we sat together and thought, okay, so if delta G is the difference of before and after, what are the factors that we really have to think about and to include into our computational assessment that we wanted to redo and revisit? So delta G is a function of what? Of course, H bonds. We know that hydrogen bond networks are really of utmost importance. However, we need new or other H bonds, better H bonds, to improve on affinity. If we just keep the H bonds that were there before, then we don't win anything. So always keep in the back of your mind that it's always the difference that counts. Then, of course, there are other terms like clash, desolvation terms, torsion energies, pi-pi interactions, pi-cation arrangements, halogen bonding, and whatever it is. And let's now walk through those and see which of those are really the most important ones. So I will spread importance blobs in green here over those interaction types. Of course, new beta H bonds are very important. Likewise, clash we definitely must avoid. We cannot have clash. These are very strong energetic terms, so they are very important. Desolvation terms, we have learned over time that these are really important to include. We cannot neglect them. So also 3 blobs. Torsional energies are usually somewhat smaller. Of course, there are exceptions from the rule, but on average, they are not as important as clash, for example, of course. And in a third category, I'd classify the weaker interactions, pi-pi interactions, pi-cation bonding, halogen bonding, and things like this. Of course, again, there are exceptions from the rule here. There can be very strong and very important halogen bonding interactions in some of the targets. But if we want to get a new go, then we thought that first we would neglect those here and have left them out in further computation. Please keep in your mind that pi-pi interactions, or pi-pi arrangements, I should rather say, can also be extremely dominated by desolvation terms. So if you approach 2 phenyl rings to each other, of course, you will have to displace the water at some point between those 2 phenyl rings, and this definitely gives a contribution which is favorable. So by the desolvation inclusion, we can already definitely describe a big part of what we see in pi-pi interactions, for example. Likewise for halogen bonding. I would have examples, but currently time flies, so I'd rather keep going. And just send us an email, and we'd be happy to discuss this in detail with you guys. So starting out from here, seeing that these 4 here are the most important ones, we thought, okay, can we somehow find something which doesn't really need a parametrization? And this is when Hyde was actually born, and there is the literature reference down here. So first talked about at an ICCS conference in 2008 in Noordwijkerhout in the Netherlands. And the most recent publication with lots of references in there is from 2013, volume 27, page 15. And Hyde actually comprises only H bonds and desolvation terms. And the reason for only including these 2 is that we can relate those 2 energetic terms through one functional kernel, namely the log P, an atomic log P description, and by this evade the necessity of actually parametrizing these 2 versus each other. So there are no weighting parameters in here. We can simply say this as a function of log P plus this as a function of log P, and that's it. On the other hand, there is no possibility to express torsional energies or clash terms as a function of log P's, of course, which is why we have decided to implement a pre-optimizer in the software, and you've seen how this is fast, that tries to minimize clash and minimize torsional energy strain. And in return, that means that Hyde energetic computations are, from a formal standpoint, only valid if clash and torsional energies are low. So you may want to keep this in your mind. So if you still have considerable clash for whatever reason it is, or if you have a totally distorted compound, then the Hyde values should be treated with caution. But never fear, we'll also give you help when it comes to torsions. I'll give an example in a second. So I'd like to jump into the next demonstration here, a recent example from bioorg MedChem Letters 2008, where there was a nice publication about magic methods here, 3-IPH. So I'm jumping into CSAR again. This is right here. I'm downloading 3-IPH. And I'm just quickly cleaning up the target so that we start out with something new. Pressing del on my keyboard, and here we go. So that's an empty protein currently. Now we are going to load in the unsubstituted ligand. So I add ligands, and I go to my demo directory, 3-IPH, no methyl, an SD file, which is right there. Everything already done in this. So if I click on this guy here and zoom in, we can see what happens. We again see the coloring. We see something red, and the rest is mostly green. And we can now go into the editing mode in a second and modify this guy here. So stopping here for a second, actually using the labeling function, which is in the lower right here, checking the label, we can now actually click on these atoms and see what's going on. And you see there is a ligand column and a receptor column, a desalvation line and an interaction line. And with these values here, you get a feeling for why this atom is happy. You see that before we can actually form an interaction, we have to pay desalvation penalties. We have to pay 10 kilojoules roughly to free this carbonyl oxygen from the bulk water in which it was floating before. And we win back only minus 10.4, so that doesn't even suffice for an overcompensation. On the other hand, from the receptor side, we see this backbone NH functionality here, for example. We have to pay 4.9, roughly 5 kilojoules. So don't take the post-comma digits too seriously here. And we win back minus 8 something. So overall, if I sum up these four values here, I arrive at minus 3.3 kilojoules. And clicking on the I will tell us what receptor atoms are actually involved in forming this interaction. I'm slightly turning this around so that you get a better feel for the 3D situation here. And I can toggle this back. Okay, so you could do this for every atom. Now, the nitrogen is pretty red here. We can again go and check what's going on. Label, click on here. We only pay desalvation, but we do not really form an interaction, so we do not win anything back. I should say that this is pretty much spot on here with experiment. So it has been measured to be 2.5 micromolar. So it's roughly in this regime here, which fully overlaps with the error bar that we compute. Okay, so let's now try to modify this ligand. I'm jumping into the edit functionality, which is this guy up here. So this edit button, and I'm going to click now, which changes the view a little bit, and you can see that there is whitish fog around the ligand, telling us where there is room to improve the tightness of fit. And so if I turn this around a little bit like this, we can see that there is room for at least a fluorine atom. This is what the fog encodes, at least room for a fluorine atom right in this area here. So we could actually try extending this and putting a methyl here. And this is exactly what they did in the paper. So the editing works in such a way that you first select and then act. So we select this guy by clicking on it, and now I can press C for carbon on my keypad, or alternatively, I can go to the element selection functionality on the right-hand side. But since it's so much fun to just press a C on the keyboard, I'll do this now. And you see that we do an in situ optimization here, a very quick adjustment of bond lengths and angles, etc. And the fog has vanished. So now we have optimized the tightness of fit, and I can actually click on put this back into the table, which is on the right-hand side here. Hopefully you all see that. So I click here, which triggers the computation of the affinity estimation on the left-hand side. And actually, this compound has been measured in experiment to be roughly 12 nanomolar active in an Ki experiment. So I'm exiting the editor here to see what this gives. And as suspected, we now see a very nice big green blob around this methyl here, reflecting how this activity increase has actually occurred. Another thing that I would like to point your attention to is the fact that we have a torsional difference here, and I'll jump back to the software in a second. So you see that there is something yellow and that there is something red over there. So jumping back to CISA, we have a toggle at the lower left here in the very southwest of the software where we can toggle between the height visualization and the torsional visualization. I'll talk about these torsions in a minute, but if I toggle this, you'll see that we can actually color the rotatable bonds here with respect to how often they occurred in small molecule crystal structure databases. And in our case, we are happy to tell you guys that we could negotiate with the people from the CSD, so CCDC people in the UK, and actually we can include this coloring which relates back to statistical occurrences of these torsions. Here we can expose this in the CISA software. And actually this is currently further being pursued by Roche in Switzerland and ourselves. And so this is not at all dead and will be refined in due course. So green means this torsion has been very frequently observed in the Cambridge structural database. A red means that this is very rare, and a yellow means that this happens sometimes but not too often. So let's take a look at what's going on here in red. That's an amide bond, and you can see that this amide bond is out of planarity with the aromatic system back here. So this is why it's red. This is really rare. On the other hand, we have something which is not super rare, but sometimes observed. This is why we color it yellow, namely this arrangement here, so the rotation around this bond. However, if we go back to the original ligand that we started out with, which doesn't have the methyl, then this scenario here is red. And you may know from your early days of chemistry that these unsubstituted aryl connections should be in plane. So this is definitely something where you should be alerted, maybe even at the crystallographic state, where you could say, does that really comply with the electron density that I found? So going back to the slides, yellow means unusual and red means very rare. So what we have spotted, besides the fact that the energetics look as if we could really win quite a lot of energy by adding a methyl here, and this wasn't really about just making it more greasy. It was really filling a pocket, tighten the fit. In addition, what votes strongly for this to be a good idea is that we lock this torsion here into something which is much more preferred compared to the plain red rotatable bond that we had in the initial case there. Okay, so we call it torsional significance. It has been written up with Roche and Hamburg University. Actually, I forgot to put a proper reference down here, but if you search for that, you'll pretty quickly find the respective publication. Green means frequently observed in the CSD, yellow unusual, red very rarely observed. This is a statistical and not an energetic statement. So, of course, people tend to think what has been observed often should also be energetically low and the other way around, but there are definitely exceptions from the rule. Okay, with this, I'd like to quickly jump into a few of the published applications that you can just have a dive at on our website. On the CISA website, you'll find a science tab, and under the science tab, you'll find the literature collection. Even though it's new, we already have a few of those publications here, including, of course, the theoretical papers up here. But also a few external applications have now emerged with the software. So one first example that I would like to give to you is from Groningen, from Anna Hirsch's group. And Anna is really a brilliant mastermind here. She had a publication in Angewandte Chemie in 2014, and they joined dynamic combinatorial chemistry and structure-based design. And this is a MedChem only group at the University of Groningen. So there are no computational experts actually around there. The idea was that they let fragments combine into ligands reversibly. So you have all those fragments in here, and you find a proper connection possibility between those that is reversibly open and closed, and that can be done in situ. They found that the acyl hydrozones were actually the ones that they wanted to keep on working with. And once they had these in solution, they added a protein and did a binding detection using saturation transfer NMR. And then they further optimized these structures. Currently, what comes out there is in the writings, as Anna told me a few weeks ago. So here's the protein, you add this, and the protein essentially selects the fragment combinations that it likes. The modeling contributions here was actually to look at what could fit. They used tools like Moloch, our good FlexX there, and hide affinity estimates. They selected relevant binding sites using software from 3 that they observed after soaking. And actually, this was confirmed by experiment. And that's also described in the paper. They did soaking experiments with lower concentrations, and only 1 of these binding sites actually survived. And of course, they did a lot of plausibility checks and estimation of activity along the line. So what happened? From 25 acyl hydrozones, they spotted 8 binders, and the 2 best were low micromolar binders. That's okay for a fragment, really. All PDB structures are actually available there for you guys to look at, and all work beautifully within CISA. And these 2 here were further elaborated. Just keep in your mind 3 and 5 and 4 and 4. And if we look at the activity relation between experiment and computer, we see 6 and 3 in micromolar, that is, and 7 to 28. So at first sight, you would think, okay. But keep in your mind that definitely there are experimental error bars as well. And when I talk to the experts, they usually tell me a factor of 3 down and upwards is what has to be taken into account realistically. And with this, we slightly undershoot here, but seeing that this is a computation which doesn't even last a second, that's pretty good. And especially when it comes to seeing where there are problems, issues, etc. So for example, this guy here, where they actually had 1 ligand in this pocket, but as it appeared, this was a concentration artifact from the soaking, which was confirmed in recrystallization. And the relevant binding mode was actually the one below here, onto which we overlaid the redocking experiment, so or the docking experiment, if you care. So the docking properly spots this with the hide affinity estimation there. And the visualization is even more important in my opinion, because here you can really see where to optimize these compounds. Again, green is good, red is bad, and again, we are really pretty much spot on here with the method. Torsions are unusual, but not red. So yeah, so far so good. And for example, this structure here shows you the naphthol moiety of this 3,5 combination compound. And what you clearly see is there is a carbon facing the carbonyl. And of course, that's a very unfavorable arrangement, because you pay a lot of energy from the receptor side, and you only win a little bit back from the ligand side, because there is a carbon from the ligand side. And of course, they are optimizing at this very point here. So it's always nice to get this visualized in almost no amount of time. Another example, very quick example that I want to go through with you, is a paper which appeared in late 2013 in bioorg MedChem. And here they assessed COX-1 and 2 selectivity issues with various binders. The modeling support here was used with respect to scrutinizing crystals. They used hide and FlexX. For the selectivity profiling, they used docking and then hide. I'll have this on the next slide. And they also spotted the IDs of relevant interactions for further optimization. So, as you can see here, these 4 compounds, how should I say, scaffolds, had various flavors with respect to the R groups here, R1, 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 R1. And this is taken from the publication, and in 11 out of the 12 cases that they looked at, height really gave the correct trend, although we have to admit that here and there we overshoot with a systematic error. So definitely something worth looking at. Interesting application of this function here. A third application that I would like to quickly comment on is on understanding SAR, which wasn't really so obvious. So at Bonn University, Nikolai Tsvetkov and co-workers spotted extremely active, sub-nanomolar active MAOB indazole inhibitors. But what wasn't really fully clear at the outset of the project was how come that the C5 substituted indazoles would bind even stronger than the C6 substituted ones. So what was done is a docking simulation, visual inspection on what the relevant binding modes really were and what was interesting and not so interesting. And what appeared was that, and this is a kind of older color variant in the software, which is still available in our traditional package for structure-based modeling, which is called LEADIT, L-E-A-D-I-T, LEADIT. What comes out is that this C3 at this position here really contributes nicely with the desolvation gain because it's facing, or it's relatively close to the phenylaniline 343 here, as opposed to this scenario here where the nitrogen comes to lay, and this nitrogen simply doesn't get that desolvation reward that the carbon on the 5 substituted indazoles gets, and therefore this binding here is much stronger compared to the other side here where it's much weaker. So, taking a little break here, we would hope that you find it useful to use CSAR and HIDE for scrutinizing crystal structures, use the alerts in there, check the geometries, take a look at the torsions. Does it really make sense to model it this way or that way? Maybe give feedback to your crystallographer there, or yourself be made aware that perhaps it might be dangerous to continue this path or that path. Use the torsional alerts as mentioned. Take an informed selection of chains and multimers. I didn't really comment on this too much, but often when you use multimers and feed them into CSAR, you can see that one chain performs a little bit better than the other one. This is because, of course, not every crystal or every crystallographer achieves total symmetry in multimers in the modeling. And as Derek Lowe once put it, we always tend to believe that PDB files are a message from God, but of course PDB files are only just models of model outcomes of an electron density that has been recorded experimentally. Rationalizing, maybe even predicting SAR. So I'm not aware of any other tool which is really able to visualize desolvation. That's definitely a very unique point about CSAR. Assessing selectivity estimates, as you've seen in one of the publications that I referred on. And of course, checking poses, checking dockings, get a feel for what could be right, what could be wrong. And there is more to come. Maybe at this point, I should just quickly mention that the way how we develop things is not like we make a 3-year plan and then we just code it down and then we do a release, but quite the opposite. We carefully listen to you guys and are extremely interested in what's really your next big challenge, what's really of utmost importance, and then we try to implement this as good as we can with as much workforce as we have, and then we do a quick release. So seeing the fact that CSAR is out for 1 year only, 10 releases really tells you a story. So with this, that's an introduction to my next poll. I would like to know from you guys what in your mind is missing most. So we have a few examples that we think could be worthwhile. So take a look at the question on your screens. Should it be something fragment-based ligand design, like link, merge, do an R group exploration, or are you interested in covalent binding? Would it be interesting for you to use ligand-only methods? or I need more 2D visualization. So maybe a few of you have seen that we have pose view, which does a very neat atomic display of protein ligand complexes in 2D, and so on and so forth. So we have 45%, 50% who polled. Just give us a click. 70% polling. And we seem to converge with a pretty strong focus actually on linking, merging, arc group, exploration, and so on. Still followed on rank 2 with covalent binding being very popular currently. The rest is between 5 and 10% ligand only 2D visualization and reporting. Okay, thank you very much. That is really very useful. So 7 minutes before we should close, actually. How would you guys get it? Actually, you can just download it, and there is a 7 days license included, so you have full functionality. If that expires and you still have not found enough time to actually test it, just download it again. Here are the respective links. There is a homepage for CISA, which is www.biosolvit.de or com/CISA. The download page is at biosolvit.com/download. And we have social networks. All of them are essentially there, but the most prominent ones are LinkedIn and Facebook. So biosolvit.com/LinkedIn and facebook.com/biosolvit are the ones that are probably the most important ones to you guys.
Marcus?
So with this, I will leave a little bit of room for questions, and not sure what is in the checkbox here. We'll assess this in a second. We do appreciate your time. We know that it's often not easy just to dig oneself out of the work that there is, and to find the time to actually spend an hour in front of the screen and listen to somebody telling stories. So thanks very much appreciated. Just a quick reminder, there will be another Biosolvit webinar soon, in almost 3 weeks, which will be on target focused library design made easy. And soon you will be able to register under the events page on our homepage. So once more, thank you, and over to Carsten.
Yeah, there have been a few questions here. Post into the chat box. So the first one is, homology models are known to vary from X-ray structures. Do we have a method of making out how correct the predictions are without the actual experiment? And how do we account for allosteric binders?
Okay, so let me focus on the first one. So there is not really a numerical value that people can just rely on to see the quality level of something also. But I'm just trying to give you an example here. I'm downloading a structure. Oops, excuse me. I'm downloading a structure which has been recently published by Roche, and my my advice to this, or the help that the software can actually give here, is the following. So first, if you have something co-crystallized or something modeled into a model, it's always good to just jump into the structure and take a look at the intra-protein hydrogen bond network. If that is of low quality, you should be alerted, and often this also gives hints on where to optimize a homology model. So take a look at, for example, these guys here. A dark green means that this is a geometrically very favorably formed hydrogen bond. So the more dark green we see, the more concise the structure should usually be. So we see a whitish here, a plain white there. We see an almost whitish there, light green, and so on and so forth, which overall already alerts us a little bit about the quality of the structure. And indeed, the electron density is pretty dim down here. And also, things look a little bit awesome, odd up here. For example, this scenario here, I'm zooming in onto this guy here. There is actually a very classical arrangement, which is like an amidine arrangement here, CNN versus a carboxylate here, but the hydrogen bond is simply not formed. And take a look at why. I mean, this is geometrically just simply not feasible. The angles are just not compatible. So this NH function points upward, whereas the COO function is much, much lower in plane. And the electron density would easily allow to model this a bit further down below, so that these two NHs can really form each a separate hydrogen bond there. So just the fact that you have an NH in white here instead of a nice green line here gives you a hint on where this homology model could actually suffer. In terms of allosteric binding, the last example that I gave you from Bonn University was actually, no, that wasn't really an allosteric binder. But for allosteric binder, there is no limitation at all. So since there are no parameters in the system, height and CISA are equally applicable to allosteric binding. On the other hand, what we have not yet included is any sort of protein flexibility. So this is definitely something that you would have to worry about for the time being in other software, probably operated by your computational specialist, or ask us for help. But in CISA, it's currently not yet included, so that could be very relevant for allosteric binding, of course. But the mathematics and the model behind the scoring isn't really a limitation with respect to any sort of binding. People at Bayer also use it for protein-protein interactions and more. Yeah, why not?
There was another question: from where do we get the insight that a methyl would be a good substitution to fill the presented fog?
Oh, that's a good question. Well, essentially, this is just by playing around with it. Let me just open this thing again that we just had there, 3IPH. So the fog is interactive. I'm again emptying this so that we can get a better feeling for things. So taking out the crystallization add-ons, etc. Loading in this guy again and hitting edit. By the way, you can use the space bar to actually center the molecule in the view. So let's say we had we wanted to extend this compound back here on the cyclopropyl ring. We could again say that's a C, and you'd see that the fog still extends a little bit. So you could even try to give to make it another C there, and now it vanishes. So from the behavior of the fog during editing, you get a feel for how big your moiety actually could be that you use there. Of course, the idea that you may have is that the software proposes a bunch of building blocks automatically and proposes the ones that you should perhaps start with. This is something for the future, which is currently in our ponderings. And this is what I refer to our group exploration, the poll at the very end. So for now, it would be playful and interactive, and up to you with your medicinal chemistry expertise to actually find the ones which fit best and score best.
There's another question. Free energy predictions are not very accurate, but can't enthalpy be predicted by itself?
Well, in the mathematics that I tried to explain on the earlier slides, it may not have been really clear what's in there, but essentially the height model using the log P's in there, the before and after consideration, has an automatic inclusion of both enthalpic and entropic terms. If you want just a plain enthalpic estimation, you would probably be good enough with a good force field. On the other hand, we have, if there is one thing that we really have learned in terms of scoring functions during the last 10 years, then it is about how important desolvation terms are to include. And desolvation also alludes to the thermodynamic effect. So remember when grandmother cooked the soup for you and the soup was all cold, you had these, what we call in German, the greasy eyes on the soup, and these greasy eyes pop all up and become very small greasy eyes upon heating the soup. So this is definitely something which needs to be taken into account also in terms of binding. So I personally see a strong advantage in using both factors in any sort of scoring. So I'm actually pretty happy that using the log P increment system, we capture both effects in a way. And And I would include this, and I would I would suggest you actually also include these.
Would be
It's a formal approach as opposed to a long-lasting modeling simulation that a few other groups currently pursue, the free energy perturbation approaches, or be it MMGBSA methods, and so on and so forth. So this formalism, even though it just needs a fraction of the time, is roughly as accurate from what we've seen so far.
And it would be pretty dangerous to omit the entropy in this case as well. So it's good that entropy finds its way into the HIDE approach as opposed to other methods. There was another thing. Can we use this with 3D glasses? Can you quickly show how to engage the 3D mode?
Yeah, currently not all stereo hardware is supported. There is a settings button here, so I exit the editor. There is a settings button here, and under display, you can see that there is currently support for polarized 3D glasses here. So if you have the NVIDIA technology, for example, then we are currently not yet fully there, but it would be interesting to have your feedback, and always great to know if you have different technologies so that we can put somewhat higher priority on these things.
Okay, that's it in terms of questions.
Okay, brilliant. Then maybe once more the slide on where to get it. And yeah, we'd be happy if you played around with it a little bit and gave us feedback. And although I cannot disclose something like a list price here in the webinar, we assure you that it is very reasonably priced, and just contact us if you need to know more about pricing, etc. Okay, thanks everyone, and hope to see you very soon on our website, in our next webinars, in person at a conference. Let us know, become our friends on Facebook, and stay in touch. And we hope you have a great evening, great day, wherever you may be. Thanks once more, and take care, you all.